Greetings everyone. Welcome back into calculus. We're going to talk about an application of derivatives here. It's called optimization, and the idea is to find the best of something whenever you're having some sort of situation and you want the lowest cost or the most profit, or the place at which a height peaks out on a rocket, or anything where you just want to find the absolute extreme of something. And we've actually already talked about all of the actual calculus that goes into this when we talked about finding the extreme values of functions on closed intervals, because that's really what this optimization is. It's just an application of the extreme value theorem. Well, you should be able to find a closed interval. You should be able to find a maximum and a minimum of the function on that closed interval. And basically the only difference here is you just have to construct the models yourself rather than the functions just being handed to you all the time. Okay, so let's get started with some examples, because that's pretty much all there is to this. You just got to practice and get used to putting together the models. So first one out the door, find the maximum value of m, where m is calculated by doing 6 times x squared times y, and x and y are restricted to being non-negative, and x and y have to sum to 51. So what you'll find in most of these situations is that you'll have a constraining equation or equations, and then you'll have your optimizing function. Okay? Can you tell which is which? The constraining equations here are these bottom three, okay? They're just telling me the rules of the game. And then the thing that I'm optimizing is the thing that it's asking for the maximum value of, right? So m equals 6x squared times y. And what I want to do is I want to make a function of just one variable if I can help it. Okay, so here for m, if I can make that into a function of one variable, then I can apply all of the calculus that we've been talking about here, right? So then this is the constraint equation right here is going to help me do that. X plus y is supposed to be 51, right? Well, really what this is handing me is a way of rewriting y so that it's something that depends on x, right? If I subtract x, y is 51 minus x. Then I can take this and substitute it for the y in my calculation of m. Then that means I have m as a function of x. It would be 6x squared times 51 minus x. Now that I have an actual function, well, then I can follow the instructions, find the maximum value, okay? I've already got one end of my closed interval as well. Remember, we want to have a function on a closed interval if we can help it, okay? It's okay if you have an open interval. A lot of times these questions are only going to have singular answers anyway, but it helps to make sense of it. Notice x has to be greater than or equal to 0. So for my function in this case, I know at least that x has to be restricted like this, right? Let me separate this here. I know x has to be restricted to that. And then think about it. Y also could be 0, and that's the minimum, right? So I can't have x any bigger than 51. If x was bigger than 51, y would be negative. So therefore, I can say that that's definitely, for this problem, the closed interval that I should use for this. However, you should already be able to tell that both of these endpoints are going to be minimums. You can tell right away. Look, if I plug 0 in for x, m is going to be 0. It multiplies out. And if x is 51, y is 0. Again, multiplies out to 0. And that's going to be the lowest m can be, right? Because y is never going to be negative, and x squared can never be negative, right? And x is never going to be negative either. So 0 is definitely a minimum, and that's going to happen at these two endpoints. What you'll find in all of these problems is that usually the endpoints are not the thing that they're asking for. Typically, that's the way these things work out. If you have a closed interval, typically the endpoints are the opposite of what they're asking for. No, there's always exceptions, but... Okay, so let's find that maximum point. Well, remember, besides endpoints, I also have to check critical points. So that means I need to find a derivative. To make this easier, I'm just going to multiply it out first. M of x is going to be equal to 306x squared minus 6x cubed. So my derivative, m prime of x, is going to be equal to 612x minus 18x squared. And this is never going to be undefined, so I'm not worried about undefined critical points. So I'll do the equals 0 kind. 0 equals 612x minus 18x squared. I can easily solve this one by factoring. So I'll factor out, let's see, I can get at least a 6, I know, right? If I pull a 6 and an x, that's going to leave me with 102 minus 3x, minus 3x. I actually could have pulled more. Yep, because 3 comes out of 102, 34 times, right? So I actually could have pulled an entire 18 here. Yep. So what this is telling me is that either x is 0 or x is 34, right? Well, we've already established that 0 was probably going to be a minimum, right? Okay, but according to the extreme value theorem, if I have a function on a closed interval, I just have to find the critical points and the endpoints, and whichever one is the highest is the maximum. Okay, so really, since 0 came up as a critical point and an endpoint, I only need to check it once, right? M of 0 is going to be 0, because look, you plug in 0, you get 0. M of 51, we already attested to that one too, right? 51 minus 51 is 0, so that's going to give 0. What about M of 34? Well, then I would have to do 6 times 34 squared times 51 minus 34, which would be 17. Oh, nice. So really what this is 4 times 17 cubed, right? Because not 4, 24, because the 2 and the 2 from the 234s makes a 4 times 6 is 24. And then I have 17 times 17 times 17, which comes out to be 117,912. After you cube 17 squared times 17 is 24. Yeah. Okay, so obviously this value of m is higher than the other two. So this one is the max value, right? And we also found the maximum value, right? We found the maximum value of m. There it is. Which values of x and y made that happen? Well, we have x equals 34, and therefore y equals the 17, right? So sometimes it would ask what values of x and y maximize it, in which case the answer would have been the x equals 34 and the y equals 17, okay? Here the question said find the maximum value. There it is, right? Okay. Next example. Which point on this function is closest to some point on the grid? Okay? So sometimes you may have a model, or you may have some sort of pathway or whatever on down the line in other calculus courses, or maybe in an engineering course, who knows. But I need to find a place on this path that has the least distance from something. Okay? All different applications need something like this. We'll just start this with a line. A lot of the other things are doable with other functions, but they require a lot of other equation solving. So let's just get the idea down for this one here. Okay? Which point on this function is closest to the point negative 2, 5? So what is the optimization function and what is the constraint equation? I know it's tempting to say f of x. It's a function, so that must be what I'm optimizing. No, it's not. The point on f of x, the fact that the point that you're finding is on f of x, means that f of x is the constraint equation. You are restricted to just these points on this line, right? Okay, so then what's the optimization function? Well, what am I minimizing here? Closest, right? I'm minimizing the distance function. It's not written up there, but that's what it's asking me to do. So what's the distance function? Well, it's just the distance between 2 points, right? Distance between 2 points, square root of x minus x squared plus y minus y squared, right? Where, it's like x2, x1, y2, y1. Just a plain old distance formula, right? Well, I have a location, a point, negative 2 and 5, right? So I've already got a negative 2 and a 5 that I can plug in, right? But then what about the other x and the other y? Well, that's supposed to be the point that's on the function, right? So for that, I'll just be plugging in x to represent the x value of the point I'm finding, and not y, right? I can calculate the y from the x. I'll plug in f of x to that other y value, because f of x is a y value, and that's the constraint. That's just like me solving for y here and then plugging that back into the other function, you see? It's me having a way of having a relationship of the y into the calculations involving x. So my distance function d of x is equal to the square root of x plus 2, quantity squared, right? X negative negative 2, plus the function is negative 4x plus 9 minus 5 squared. So let's simplify this out a little bit, right? Let's make it look a little bit neater, because we are going to have to do some calculus on this thing. Square root of that's x squared plus 4x plus 4 if I multiply this out, plus here 9 minus 5 is 4, right? So that'll make it easy for me to FOIL that one out too. I'm going to get 16x squared, and then I'll get negative 4x times 4 twice. So that's negative 16 is negative 32x. And then 4 times 4, I'll get 16 again. So my distance function of x is equal to the square root of 17x squared. 4x minus 32x is minus 28x, and plus 20. All right. So that is the distance function for any given point on the line directly to the point negative 2, 5. So remember what that means is if I pick just any point, right, on the line, the distance from that point to negative 2, 5 can be calculated with this function. And all I need to know is the x coordinate of the point that I picked on the line, right? And that could be for any point, even the point over here. So right now, I don't actually have a closed interval for x. I can actually pick any x on the function f of x. So all that means is that I can't apply the extreme value theorem, right? But common sense of the picture tells me there's only one minimum, and it's going to happen in this picture. Look at it. It's going to happen right when that is perpendicular, okay? It's going to happen right here where this line, the distance from the point to the function is going to be perpendicular to it, okay? So what that means is I know that there is a single minimum in there, and there is not a maximum, right? There is no maximum, because I could go as far out on this line as I can imagine, and the distance just gets bigger and bigger and bigger. But that's okay. I'm not looking for a maximum. I am looking for a minimum, right? So the minimum must be a critical point of my function here. Let's go ahead and do the calculus on that. So I'm going to take the derivative. And remember, this is a square root, right? So it's really just this whole mess to the 1/2 power. So that means it's 1/2 17x squared minus 28x plus 20 to the negative 1/2. That's the outer, right? Got to do a chain rule here. Times inside derivative is 34x minus 28. Let's rewrite that and set it equal to 0, right? Because I'm looking for a critical point. So I'm just going to go ahead and set it equal to 0 here. I've got in the denominator, I've got the 17x squared minus 28x plus 20 to the 1/2 power. And you could rewrite it in a square root if you want. Okay? And then 1/2 I can actually distribute into this, right? Because I can just do the 1/2 times that. And that's going to give me 17x minus 14 for my derivative here. Okay, now of course it's a fraction. You could say, look, we can get some undefined critical points. Absolutely we can. But notice that's where this piece is equal to 0. And that's exactly what we were saying earlier about the domain of this function, right? Where this inside piece is equal to 0 are the edges of the domain of this function, okay? So that means that where this is equal to 0 is where this distance is going to stop functioning, okay? If you want to, find a silly word for it. This this particular function has its endpoints there. Now what I'm going to do is I'm going to set this equal to 0, which means this multiplies away. And I've just got 0 equals 17x minus 14, which tells me that x is 14 over 17. So I've found an x coordinate for the point on the graph. And look, it's right about where we guessed it was. It's somewhere really close to the y-axis right here. And I mean, of course, I'm not doing this to scale, but it's about the right idea. So 14 over 17 is my x. It asked for the point, right? Which point on the function? So far I have this, 14 over 17. How do I find the y value that goes with that? Well, I just plug it into the function, right? I would have to do f of 14 over 17, which would be negative 4 times 14 over 17 plus 9, which would be negative 56 over 17 plus, I want to get a common denominator here, so 9 times 17, because I'll do 17 over 17 here, which will be 90 and 63 is 153, right? So then minus 56 will give me a total of 97 over 17. Okay. So the other coordinate to the point is 97 over 17. So that's the point that's going to be closest. And yes, I could have thrown a lot more stuff into this. Like I said, you can find the domain on this function, and that would actually give you your interval, okay? And it would be actually a closed interval, mind you, because the square root of where this is equal to 0 is, of course, 0, right? But we're not interested in the endpoints of the domain on this one. Those are going to be the opposite of what we want in this case. That's just going to tell me where the function works. What I really need is to have this value. Now, here's another side question. What if someone says, hey, how do you know that's a minimum? Well, there's other ways of proving that. If you recall, we have a theorem for the second derivative test, right? If I have something that has been identified as a critical value, all I need to do is find the second derivative and plug it in, okay? Long story short, what's going to happen is your main part of your second derivative is going to come out in the terms of these this positive number here, 17, and you're going to find that it's concave up at this point, okay? In so doing, it makes the 14 over 17 a minimum. But FYI, if you were to try and do the domain on this, you would find out that this particular quadratic doesn't actually ever equal 0. You'll get your imaginary values for it, and that's really the whole reason why this thing can have this minimum, because it's going to be sort of like a parabola, but the square root sort of dampens it, and you're getting the minimum value for that. Okay, so. The domain on that is not important information just for this calculation, but if it makes you feel better, you can figure it out and see that it actually is all real numbers. You can also do your second derivative, plug in this critical value. You'll see that it is concave up, which does actually cause this to be a minimum, and what you have is the point where the distance is the minimum.
Let me give you a visual to go along with that last problem. Here's the function y equals negative 4x plus 9, and here's the point that is in question. We're trying to find the point on this line that's the closest, the shortest distance to this point B right here. So notice that what we calculated was the point 14/17, 97/17 right here at A. So if I take the segment here between those two, you can see it's listing that distance as 2.91 here. Okay, so if I take any other point on this line, let me just call it E, whatever, and then look at the segment length. Right now it's at 3.5, and if I move that point all along, you can see the length of that segment changing. Right? See, now it's at 4.5 because I'm moving E further away. Notice as soon as I get parallel with A, it's exactly the same, 2.91, and then it starts increasing again. So you can tell just by observation here of these distance calculations that A is in fact the closest point. Another way to tell is that if I were to take the angle between the line and the line that connects these two, they're at a 90-degree angle to each other. That's the red line here and the actual function line. The fact that those are perpendicular means that it's at its maximum turn away from it, right? So then when it starts to turn back again, it changes back in the direction that it used to be. Okay, so those are some indicators that show how you can guess that it is, right? But remember, we actually computed also that it was this minimum point. And we did that by creating a function y equals the square root of 17x squared minus 20x plus 20, 28x plus 20. Here's that function. Notice it does actually have this minimum point that this thing was so nice to calculate for me. It happens at 0.82, which you'll notice is the 14 over 17. and it calculated the 2.91 distance, which is that minimum distance that we already have seen.
More examples of optimization. Here's a couple of common ones. Minimize a surface area and maximize a play area. All right, so this one right here is strictly just knowledge of formulas that go along with the cylinder. Minimize the surface area given that the volume must be some set amount. Okay, this sounds a lot like say a soda company wants to minimize the size of its cost in creating the cans, or maybe a soup company, right? That's the Coke cans are a little bit more complicated, but let's say the soup companies, right, want to minimize their cost, so they're going to minimize the amount of metal that they need by minimizing the surface area while still keeping to a certain volume of soup that they always want to sell. Okay, so let's minimize the surface area given that the volume must be 10 cubic inches. Well, okay, so I've got my volume of a cylinder and I have my surface area of a cylinder, right? Which one is going to be the constraint equation and which one is the optimized function? Well, we already said we're minimizing surface area, right? So this is the one I'm going to be turning into my function. And I have an actual number in for volume. Okay, so real quick, we can tell that 10 has to be equal to pi r squared h. Right? That's my constraint equation. I can use this to replace either r or h. It looks to me like it would be easier to solve for h, and since there's only one h in the other equation, easier to replace. So that's what I'm going to do. I'm going to see that 10 divided by pi r squared is going to be equal to h, right? And then what I'm going to do with that is plug it in for h, and that's going to give me a function. So let's see, my function, I'll call it a of x, a of r, right? Because r is going to be my variable now, is going to be equal to 2 pi r squared plus r times 10 over pi r squared, like that. Well, let's see. I could make this a little bit easier on myself. Let me go ahead and distribute the 2 pi in also to make it look a little bit cleaner. A of r is equal to 2 pi r squared plus, now one of these r's will reduce here, and then I'm multiplying 2 times 10, which is going to give me 20, and pi over pi is going to eliminate. So I have 20 over r, right? To make this easier to take a derivative of, I'm just going to say 20 r to the negative 1. So there's my area function of r based on this constraint equation. And as usual, right, we have our limitations. Obviously, r and h can't be negative, right? Also, they can't be 0 because the volume is supposed to be equal to 10. So 0 is sort of like a low-end boundary. And the smaller you make r, right, the larger h will be. But think about it. As I increase h and r gets smaller, it's like you'll have this little bitty, circle with a really tall height. You wouldn't be able to really do anything useful with that, right? Or vice versa. If I let h get lower, then r has to get bigger. So as the h gets shorter, the radius gets bigger, and you just have this big disk. Eventually, it would be flat, right? You wouldn't be able to really do anything with that either. So the two extremes there, where h is 0 and r is 0, are definitely not usable, or are actually not attainable either. But trying to approach either one is no good. Okay? So This one's not going to really have that closed interval that I need either. But we can still find the minimum surface area, the minimum of this function, the same way we have been. I'm going to take a derivative. I'm going to set it equal to 0. I'm going to make sure I don't cross over any undefined ones. Okay? And then if we need to, we can prove that it is a minimum, right? Using second derivative or whatever. So start with first derivative. A prime of r is going to be equal to 4 pi r, not plus this time, right? Minus 20 r to the negative 2, right? Because I dropped the negative 1, subtract 1. Okay. So now let's set this equal to 0, and let's swap this around a little bit to make it look a little bit neater. So 4 pi r minus, that's 20 over r squared there. I can make this a lot easier on myself if I just multiply everything by r squared at this point. If I multiply by r squared, these will eliminate. If I multiply by r squared here, it will just combine it with the other r. And multiplying r squared here will still be 0. So all that'll do is help me out solving wise. I'll have 4 pi r cubed minus 20, which I can now easily solve for r. Right? Add the 20 over, divide by 4 pi, and I'll have 5 over pi is equal to r cubed, which tells me that the third root of 5 divided by pi is equal to r. Right? Let's crunch that up and see what we get. Pi is a crazy number, right? So I've got the 5 over pi, it's 1.59, and then I'm going to raise that to the 1 over 3 power, 1.167. So r is around 1.17, and we're measuring in inches, right? So then what height goes with that? Well, I would have to plug the r into this right here. I would have to do 10 divided by pi times r squared. So I've already got this in my memory right now, right? This is in my calculator's memory, this calculation. So I'm going to use the previous answer key on this calculation. I'll do 10 divided by parentheses pi times previous answer squared. And I get 2.335 inches. So I have minimized the surface area by creating this radius and this height of a can. So if my volume had to be 10 cubic inches, then I would let my radius be just a little bit bigger than an inch, right? The radius of the circle. And then my height would be just a little bit over 2 inches. Mind you, by the way, the radius is only half of the circle. If you were looking at the top of the can, right? 2 radii put together is about 2.34, which you'll notice is actually the same-ish as the height, 2.34, right? So it's almost like you have a square cross-section on your can there, right? Nice, beautiful answers like that come out kind of, oh, look at that symmetry, are what you should expect in these optimized circumstances. Even if the numbers aren't pretty with these cube roots and pies and things like that, you'll always end up with something nice looking like that, some sort of symmetry. Here's another common problem, and that is to create some sort of area with a fence that has some other barrier that you can save yourself some fencing. People do it with horse pens next to a lake, or pig pens next to a barn, or whatever. I chose to do a playground next to a school, right? So I'm going to put some fencing out here. And let's say I have 4 different grades that I want to keep separate, and keep all of the creepers out from getting to the kids. So I put the fence there for the school, right? Okay. So what I'm going to do is they want to know the dimensions that maximize the amount of play area that I can have for the kids. Okay, fine. So if I say the dimensions, then what I'm looking for is the depth here away from the school and the width along the length of the school, right? And I'll just call them X and Y. It doesn't matter what you call them. But what dimensions X and Y of this whole thing are going to maximize this? Well, okay, so what am I constrained to? 500 feet of fencing is my constraint. That's how much materials I have. I don't want to use less than that. I would have less area. I'm going to use everything I've got. Okay? But I need to see, all right, where am I building fence? I'm building fence along this long wall here. I'm building fences here, 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 and here. But that's school wall right there. That's already built. So I don't need anything on the top. Well, this is going to be X, this is going to be X, this is going to be X, X, and X in length. And then this whole thing is Y in length, right? Okay, so total fencing is 500 feet. And I'm adding up 5 X's and 1 Y in length. There's my constraint equation. The total amount of fencing has to give me 5 X lengths and 1 Y length. And then X and Y are going to be the dimensions that I figure out to maximize the area of the playground, right? Okay, well, what's the area of the whole playground? Length times width, X times Y. So my area is just X times Y. All right? Well, I can easily get Y by itself here. Y is going to be equal to 500 minus 5X. And then I can plug that into the area equation here, because this is the thing I want to maximize, right? This is my optimized function. These are my constraints. This tells me that I have an area function of X, which is equal to X times 500 minus 5X. You actually don't need calculus for this one. You could do this one without calculus with a little bit of algebra knowledge of that shape. Distribute the X and look at what I'm talking about. A of X is equal to 500X minus 5X squared. X squared is a parabola facing downward, right? There's a peak. You also have the constraints of a closed interval here. X and Y have to be positive numbers, right? If X is 0, that would be one of the minimums. If X is 0, this wall would be up against that school wall and you wouldn't have any play area, right? So actually X is restricted on that sense, right? 0 is sort of a bottom. But also, what about when Y is 0? When Y is 0, X is 100. So I'm constrained there too, on the upper end. If I find that I used 100, that would be 100, 200, 300, 400, 500. That's all my fencing. All of the fences would be next to each other, and you would have 0 play area. So, no good, right? All right, so that's my restrictive interval, but as usual, the endpoints are not the points I'm looking for. Those are not the interesting points. And again, like I was saying, this is a parabola. You could just calculate the vertex. I'm going to stick with what we've been doing, though, right? Let's keep the pattern going. Derivative is 500 minus 10x. I'm going to set that equal to 0. That's going to give me x is equal to 500 divided by 10, which is 50. So if x is 50, look at the symmetry on this one. If x is 50, then y is equal to 500 minus 5 times 50. 5 times 50 is 250, which is half of 500. So then y would be 250. There's my dimensions. The dimensions of the playground would be 50 feet by 250 feet. And of course, including the fenced-in innards as well, right? Okay? So the total 250 feet would get split up 4 ways, but I mean, regardless, that gives me the maximum amount of area. Now, what is that maximum area? Easily found if you, 50 times 250, right? Or if you plug 50 back into the original function, it would end up being the same idea, right? That would be 12500 12500 square feet would be the maximum area there. Here's another very common problem that comes up a lot in calculus classes, and it's I take a sheet of cardboard or metal or whatever and cut the corners out of it and then fold these sides that are made here, 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 and here. They fold them up to create a box that has an open top. Okay? So a box is created by doing this, by cutting the corners and folding up the sides. Find the length of the cut, x, that maximizes the volume of the box. Okay, so what's constraint and what's being optimized, right? Volume is being optimized, which is not one of my things here. So this must be my constraint, right? My original material is 60 by 48, right? And I'm actually losing some of those lengths when I start cutting the corners out to fold the sides up. And that's where the constraint is, right? I can only cut so much before it's really just cutting a whole, thing off of the side, right? So if you look really carefully, what's happening is inside of these dotted lines here is what will become the bottom of the box, right? So I have a wall, a wall, a wall, a wall, and a bottom, and then these pieces are just thrown away. And then they fold it up, okay? So what I need is to find the volume of this box. Well, the volume is going to be length times width times height, right? Volume is length times width times height. Well, let's think about this for a second. If I take this side and I fold it up right here, right? If I take this and do this, what is the height coming off of this thing here? It would have to be the little piece here, x. So the height of the box here would have to be x. All right. So then on the base here, this would be the length and the width of the bottom. See, here's the bottom, right? So the length is here and the width is here of the box. So I just need to figure out what this length and what this width is right here. Well, originally this one was 48, but I cut an x and an x. So this new measurement is going to be 48 minus 2x. That's going to be this width right here, 48 minus 2x. And then same idea, right? For the 60 here, the width is going to be the original 60 minus 2x from here to here. So then the depth right here along the back of the box is going to be the 60 minus 2x. Okay? So now what I have is that the length, the width, and the height are all dependent on the size of the cut that I make, which means I can now make volume dependent on x directly. Okay, so let's do that. Let's make a volume function here. V of x is equal to x times 48 minus 2x times 60 minus 2x, right? Okay. So then Then we're going to want to multiply this out to make it a little bit easier on ourselves. So I have x times 2880. Yeah. And then I've got minus 120. And I've got minus 96. And then plus 4x squared. So my volume function of x is going to be 2880x minus 216x squared plus 4x cubed. Okay. Also, we can throw in some constraints here, because let's think about this for a second. X can't be negative, right? And in fact, if I let x be 0, that would be an extreme case, right? If x is 0, I'm not cutting anything, and all it would be is a flat sheet. It would be nothing but bottom, no height. X would be 0, right? So that's a 0 volume, basically, if I could do that. So definitely x is bound on one side by 0. And then what would the maximum be? Well, 48 and 60, 48's the lower one, so I'll go with that one. Minus 2 times x. Well, what if x was 24? 2 times 24 is 48. 48 minus 48 is 0, right? So x can't even get past 24 without zeroing out one of the other dimensions, the length right here, right? Or rather the width, not the depth, right? If I zero that out, same difficulty, right? I'm cutting too much at that point. It means I'm cutting all the way across, because I'd be doing 24 and 24, and I'd just be cutting off the whole top. It wouldn't do me any good. Okay, so x is bound here, which means we will find something. But also, you can use a little bit more common sense too. Do you notice that my volume function is a cubic function? And it's positive, right? So then those functions tend to have this kind of shape, right? So I know that there's a maximum waiting for me in there, right? I know that there's a maximum waiting for me. Okay. So let's figure out where that's at. Let's take the derivative here, v prime, and I get 2880 minus 432x, and then plus 12x squared. All right. Well, I'm pretty sure that I can get a 4 out of everything, because 12, 32, and yeah, 88. I can get a 4 out of everything. Can I get a 3 out of everything? Because 3, 6 and 3 is 9. I can get a 3 out of that one. 2, 10, 18. I can get, okay, so if I can get a 3 and a 4, that means I can factor a 12 out. This is going to make my life a lot easier, that I can factor 12 out of everything. Oh, okay, yeah, duh, because 2880 is 48 times 60, right? That's just going to be 240. And then minus, let's see, 432. If I'm taking out 12, that would be 108 divided by 3, which would be 36. X plus x squared. Yeah. Okay, so that'll certainly make it a little bit easier for me. We could even try to continue factoring, maybe, but let's just go ahead and do the quadratic formula here, right? So basically what's happening is I want where the derivative is equal to 0. So I'm really just going to be setting this piece right here equal to 0. X squared minus 36x plus 240 is equal to 0. So I'm going to just use the quadratic formula. I have 18 plus or minus square root of 84. Okay, so let's get realistic with this. 18 plus the square root of 84 is going to be 18 plus 9 point something, right? 18 plus 9 is going to be 27. And notice that's outside of my restriction, right? If I do 18 plus the square root of 84, that's going to be too far out. 18 minus the square root of 84 would be around 18 minus 9-ish, which would land me somewhere around 9, a little bit under 9, right? Which is perfectly fine. Notice in our shape here also how that makes sense, right? If you were looking at the shape of this graph here, which critical point hits first, right? You have this one and you have this one, right? We don't want this one. What's happening is we're getting that maximum, occurring at a little bit lesser value, which is exactly what we want, okay? So between this or, let me go ahead and just write it out like this, right? Between this or this, right? This one doesn't work because it's approximately 27, okay? But this one's fine because it's approximately 9. Let's actually crunch it what it really is. 18 minus square root of 84. 8.83. That'll work. Okay, so that's what we just found. We found that the length of cut, okay, that will maximize the volume, right? Volume is going to be a maximum, is the 18 minus square root of 84, okay? So let's dig a little deeper for just a second. How do I know that's a minimum? Well, first of all, I'm familiar with the shape of the volume function, right? The volume function should have that shape. But also, right, it was the other critical point doesn't fit this. And if you really need some hardcore evidence, then let's break out the old second derivative, right? Second derivative is going to be the derivative of this, right? Second derivative, v double prime of x, is equal to 24x minus 432, right? Okay. Now notice the 18 minus square root of 84 is my previous answer. So what I'm going to do is I'm going to punch up here 24 times previous answer minus 432. Okay? And I'm getting a negative number for that. Since I'm getting a negative number for this critical point, this is a critical point, right? Since I'm getting a negative number, that means it's concave down, which means that is a maximum, an actual maximum here, right? So this is what we're saying. V double prime, this is the second derivative test for this critical point of 18 minus square root of 84 equals a negative number. I don't even care that it was 200 and whatever. I care that it was negative, right? This right here is the second derivative test telling me that this is a max point. Because it's already a critical point where it's equal to 0, the derivative is equal to 0. Having the second derivative negative guarantees that it's concave down, therefore a maximum. All right? So what size cut should we cut that maximizes the volume? Around 8.8 inches, right? Measured in inches. Yep. Let's finish up with an example that's a bit more interesting, that's sort of common and, not as much as the others, but you still see a good bit of it. I've seen different varieties of this problem, whether it be someone having to lay pipeline out to a rig off the coast, and it has different costs on land and off land and things like that. Here's a variation that I saw in the OpenStax region that was pretty simple, pretty interesting. That is a guy who needs to travel, mind you, by the most difficult means possible, walking and swimming, out to this island that's 4 miles off of the coast at a right angle, but he's 6 miles away from that right angle point. So he's going to have to walk some of the way and then swim at an angle the rest of the way if he wants to minimize his time. And the reason why that would minimize his time is even though he walks faster than he swims, it's a good bit more distance from here to here than on out. Okay, you can actually minimize your time by walking as much as you can to this certain point and then swimming. Even though swimming is slower, the distance is just that much shorter, having cut out this whole leg of the trip from having to walk it. Okay, so this is what he does. He walks to this point and then he swims out at an angle. Okay, and we want to minimize the amount of time that takes him. So there's a couple of things you need to think of here. Obviously, this is our constraint, right? All of the measurements here are our constraint. And I only need one variable in here to list out all of the constraints. I only need x. How far out should he walk, right? To find that point when he should dive in and start swimming. But then I also need to relate that to time somehow. Eventually, what I'm going to be looking for is to have some function t of x, the amount of time it takes to make the journey based on some measurement x when he jumps in the water. Okay, so then obviously he could just jump in, cut the diagonal here would be one extreme. He could just swim straight across, or he could walk all the way then swim all the way, and that would be the other extreme. Right, as far as the domain of the function. I mean, by when I say extreme, it may not be the maximum and the minimum there, but okay. So the other thing you have to remember is that with these basic type of measurements, distance equals speed times time. Right? We still have that old adage: distance equals rate times time. As far as the simple relationship between the distance that he's traveling and the speeds that he's using. And the reason why this is going to become important is because the two different modes do have different speeds. Okay, if it was just, hey, find the minimum distance, that'd be no problem. But as it is right now, because he can travel at different speeds in different modes, it kind of weights as in gives weight to one version versus the other one, right? He's a little bit faster on land, so he might want to go just a little bit further, even if it changes the minimum distance a little bit. Okay, it may not be the minimum actual distance that he's traveling, but consider that it wants to favor him walking because it's a little bit faster, right? Then we need to take into consideration the times, not just the distances. Okay, so what we're going to end up doing is saying that time is distance divided by the speed. Okay, so for the first leg of the trip, he's traveling x distance, right? Simple as that. He's traveling a distance of x. So then that measurement is just going to be x divided by 3, right? So here, t of x is x divided by 3 plus. That's the amount of time it's going to take for him to traverse the beach leg of the journey. Now, what about the swimming leg of the journey? I need to know the length, the distance that he's traveling here at this angle. Well, I'm going to take advantage of the fact that we know that this is a measurement of 4 directly distanced to the beachhead, which we can assume is close enough to a 90-degree angle to count a Pythagorean theorem here, right? That's what's going to happen here. I'm going to end up counting this as a right angle here and here, same thing, either way. And I know that this whole length here was supposed to be 6, so then this is 6 take away whatever x I've already walked. That would be the distance from this point out to the perpendicular line. Okay? So therefore, 6 minus x squared plus 4 squared should equal this leg over here squared, right? So if I call this like c right here, then 6 minus x quantity squared plus 4 squared should equal the length of that thing squared, right? But if I just square root both sides like this, right, then the length of c is this square root here. Okay. So now I'm going to take that distance. Let's simplify it a little bit too. Let's see. That's going to be square root of x squared minus 12x plus 36, right? Then plus 16 is equal to c. So square root of x squared minus 12x plus 52 is equal to c. All right. Now, that's the distance from here to here. He can travel it at 2 miles per hour, so it's that distance divided by his speed that will give me the amount of time it takes. So that's going to be square root x squared minus 12x plus 52 divided by 2. Okay, so there's my time function. The amount of time it's going to take to complete the journey given the one decision x of how far he has to travel before he jumps from the beach into the water, right? So that's what x is representing, that decision. And what we're going to do is we're going to minimize t according to that, right? Let's minimize t according to that. So I need a derivative, right? Incidentally, you may notice x, of course, can't be bigger than 6 or less than 0, right? Because those would be the two extreme versions of the trip. Obviously, he could walk past it and then swim back. That would be asinine, right? He'll at least get to this point and then swim out. So we're going to, and of course, if x is 0, right, he's not going to walk backwards. So x isn't going to be negative, okay? So x is either 0 or 6 or somewhere in between, right? So I've definitely got that restriction in there. All right, so derivative is going to be 1/3 plus. Now here's what I'm going to do for this. I'm going to rewrite this piece right here as 1/2. And instead of square root, right, it'll be this to the 1/2. So when I take the derivative, it'll be plus 1/4 x squared minus 12x plus 52 to the negative 1/2 times, chain rule, 2x minus 12. Right? Okay. And then we're interested in where this is going to be equal to 0. So I've got 0 is equal to 1/3 plus, let's see, I'll just go ahead and write it out, 2x minus 12 over 4 times the square root of x squared minus 12x plus 52. Yum. All right. So then, from here, what we need to do is solve for x, right? From here, I'm going to move the 1/3 over, and I'm going to multiply some things out. So let's see. Let's make this actually even quicker for ourselves here. Let's say that I multiply by the common denominator. Or let's just do it the way I was saying before. I'm going to subtract the 1/3 over, right? I'm going to subtract the 1/3 over. And I have 2x minus 12 is over 4 square root x squared minus 12x plus 52. And I'm going to cross multiply just to make it quicker for me. So I'm going to multiply -3 over to this and the 4 square root over to this. So that's going to give me 4 square root x squared minus 12x plus 52 is equal to -3 times the 2x minus 12 is going to give me 36 minus 6x. Okie dokie. I just multiplied both sides out there. Okay, to make this maybe even a little bit nicer on us, I can divide by 2. Look, 6, 36, and 4. If I divide by 2, this will be 2, this will be 18, and this will be 3. If I just divide everything by 2. Okay, now what I'm going to do is get rid of the square root, which means I'm going to have to just square both sides like this. Right? Square both sides. Okay. Now, since this is a 2 times the square root, it's okay to just square it separately. So 2 squared gives me a 4 times square with the square root just makes the square root go away. So I got that. And then over on this side over here, I've got the 18 minus 3x times 18 minus 3x because it's squared. So let's see, 4x squared and then minus 48x and then plus 208 is equal to, here I'm going to have 9x squared. 3 times 18 is going to be 54, but done twice, 108. So minus 108x. And then 18 and 18 is 100, is 260 plus 64 is 324. Right? Okay. So what do we have here? We have a couple of quadratics equal to each other. Right? So I'm just going to get everything to one side. Right? So minus 4, get rid of this one. Plus 48, we'll get rid of this one. And minus 208, we'll get rid of that one. Very good. So then I'll have 0 is equal to 5x squared minus 60x, and then plus, that's going to be 116. Okay. Yay, it's a quadratic, right? So, quadratic formula. X equals negative b, which is 60, plus or minus square root. Negative 60 squared is 3600 minus 4 times a. That's going to be minus 20 times 116. All over 2 times a is 10. 60 plus or minus square root of 1280 over 10. Let's see, is approximately 9.6. Is around 2.42. So obviously 9.6 is not going to work, and 2.4 is, right? Okay. 9.6 isn't going to work because there's no way he'd pass up the point, right? 2.4 sounds like it makes sense. He would walk a little ways and then he would try to swim directly out to the island after going 2.5 miles, right? And of course, the way to find that this is a minimum is obviously to notice that if you take the second derivative, it's going to be based mostly on this numerator here, because this piece is going to drop out, and it's going to be all the derivative of this one, right? And since your second derivative is going to be positive, you can expect this to be concave up, which of course makes this a minimum of the amount of time. Okay, so he would walk the 2.4 miles and then swim the rest of the way. Okay, so I hope these examples have helped you realize how to set up a lot of these things, and how the methods pretty much are the same. Even though the structures are all different, the method is pretty much the same, right? Set up your model, take your derivative, find your critical points. If you need extra information, use second derivative test, or use domain restrictions and things like that.
Here's just a real quick visualization of that function that we just minimized. As you can see, all we were interested in is the interval from 0 to 6, which would have just been between this point and this point right here. And the computer even calculated it for us. The minimum of the function t is at 2.42, which is at this point right here, right? It is only slightly lesser than this point c, but this point is the actual minimum, the one that we calculated.